Last time we saw that adding sodium hydroxide to acetic acid caused an ion exchange between the sodium and the hydrogen ions. So sodium hydroxide plus acetic acid converts into sodium acetate and water. In water, the sodium salts will be completely dissociated, so we can actually erase the sodium ion from both sides. Now, this had a big impact on the equilibrium expression because that produced more of the acetate and less of the acetic acid. Instead of adding a strong base, we could just add some sodium acetate directly into the solution. The additional acetate would also cause a shift in the equilibrium. This is an example of the common ion effect, the shift in equilibrium caused by the addition of an ion that takes part in the reaction. In this case, additional acetate would push the reaction back towards the reactants, decreasing the degree of ionization and raising the pH. So what is the pH of the new solution? We can start with a generic equilibrium expression, where the acid dissociation constant is the hydronium concentration multiplied by the concentration of the conjugate base divided by the concentration of the original acid. And if we take the negative logarithm of both sides, we end up with the pKa equals the pH of the negative log of the concentration of the base divided by the concentration of the acid. Or if we'd rather calculate the pH, that's the pKa of the acid plus the logarithm of the concentration of the base divided by the concentration of the acid. This is called the Henderson-Hasselbalch equation, and it comes in extremely handy when we combine a weak acid and a strong base, or a weak base and a strong acid to get a combination of the conjugate acid and base, or if we have separate sources for both of the ions. When the concentration of base is greater than the acid, the second term is positive and the pH rises. When the concentration of acid is greater than the base, then the second term is negative and the pH decreases. But look what happens when there's an equal amount of both ions in the conjugate pair. The concentration of the base is equal to the concentration of acid, so the quotient is 1, and log of 1 equals 0, so pH is equal to the pKa. This is a good reference point to use when deciding whether or not to use the Henderson-Hasselbalch in any given situation. Because it is a logarithm, it's sensitive to very large or very small numbers, and will only work really reliably when the concentrations of acid and base are not extremely different, which is why we didn't introduce it until now. So now we know if we add both of the ions in a conjugate acid-base pair to a solution, we could tune those concentrations to dial into whatever pH we want, especially if it's already close to the acid's pKa. We'll look at a very useful application of this knowledge next time.